All right, let's talk about two-dimensional motion. Now, the one thing you've got to recognize when you have objects traveling in two dimensions is that your vector quantities can only affect each other if they, at least in some regards, coexist within the same dimension. So for instance, if you have an entirely horizontal velocity and you have a vertical acceleration, well, that vertical acceleration does not exist within the same dimension as that velocity in any regard, right? So that acceleration would not affect that horizontal velocity. You need at least some angle on that acceleration so that some amount of that vector quantity exists within the same dimension as your velocity. So let's start by looking at a very specific two-dimensional scenario, and that is your inclined planes. Now, if you haven't checked out the notes on that yet, that would be the first thing I would do. I'd pause this video, go look at that brief little section of notes in 2D kinematics about inclines, and then come back. But so basically, if you've got an object that's sliding down an incline that's at some angle theta, well, the reason it slides down, right, and it accelerates as it slides, is because the force of gravity is acting on it. Right? But you got to keep in mind it is not accelerating at a rate of 9.8 meters per second squared. Right? Its acceleration, right, is entirely vertical if you're looking at g. Right? But g does not fully coexist within this dimension of motion, right? This plane that's parallel to the incline itself. So what you need to do is you need to break g into component pieces, where this would be g perpendicular. Well, g perpendicular does not exist at all within the dimension of this plane, right? So g perpendicular has no effect on the acceleration down the ramp. Now you'll also have a component g parallel. Now g parallel is the only component of your gravitational acceleration that is contributing to the increase of velocity of this object sliding down the plane. Now, this is a right triangle here. This angle right here, theta, is going to be identical to the angle of the ramp. So, as you increase, let's say this is our ramp, as you increase that angle towards 90 degrees, theta increases, and g parallel increases, right? So the steeper your ramp is, the greater this g parallel component is, right? Until you get to 90 degrees, well, at 90 degrees, what's your acceleration that's parallel to the incline? Well, g, right? And now you have a crummy ramp, right? It's just a wall with things in free fall. Now, as you decrease the angle of that ramp, you decrease this angle theta here, and you decrease g parallel. Right? So when you get to 0 degrees, none of your gravitational acceleration vector exists within this plane, right? And so your object is stationary, right? It doesn't increase velocity. Now, let's put some numbers onto that. So in that example 3.6 in the notes, we've got the Willamette Pass ski area in Oregon was the site of the 1993 U.S. National Skiing Competition. The skiers started from rest and then accelerated down a stretch of the mountain with reasonably constant slope, aiming for the highest possible speed at the end of the run. During this acceleration phase, the skiers traveled 360 meters while dropping a vertical distance of 170. What is the fastest speed a skier could achieve at the end of this run? Now, as we move into more complex topics like this, I highly recommend that you sketch out the scenario, right? Having a detailed drawing with your knowns and your unknowns listed directly on the image will greatly help you in processing the problem. So, let's start with just a sketch of what we got going on. And again, when you're drawing these sketches, you don't need to be, an artist. It's really just there to help you out. So if you want to draw a skier as a box, draw a skier as a box. All right. Alright, so we got our skier up there. Now, we know that he's going to start with an initial velocity of 0 meters per second. We know that the distance down our ramp that he travels is 360 meters. We also know that there's a vertical altitude drop of 170 meters. And we want to know what is his speed at the end of the ramp. Now, in order to know that, we need to know what the acceleration down the ramp is. Right? So if we draw our component vectors for g, we need to know what g parallel is so that we can determine his acceleration down the ramp, right? Because the acceleration here is going to be equal to g parallel. Now we're missing something important, right? We don't have the angle of the ramp. We don't know how steep the mountain is. But we are given two distances. We're given a distance of 360 meters. We're given a distance of 170 meters. Using this information, we can find our unknown angle theta, right? So when your math teachers showed you this, they weren't lying that it doesn't go away, right? So we got to use our trig functions. So if we're looking at this particular right triangle, right, theta, we've got our opposite side, we've got our hypotenuse, so we've got to use our sine function. Right, so the sine of your unknown angle is equal to opposite over hypotenuse. So you solve that out. So 170 over 360. And the inverse sine of that, and you get 28.2 degrees. Now make sure your calculator is in degrees and not radians while you're doing this. So what I would do is I would calculate along with me, make sure you're getting the same stuff. If you're not, email me and we can talk about setting your calculator. Alright, so we've got an angle of 28.2 degrees. Which means that this angle is also 28.2 degrees. So now we've got to look at this right triangle. We know the angle is 28.2 degrees. We know the hypotenuse, g, is 9.8 meters per second squared. We need to find this opposite side. So again, we're going to go into our trig functions. So opposite over hypotenuse. So g parallel would be 9.8 times the sine of 28.2. So 28.2 times 9.8, I'm sorry, sine of 28.2 times 9.8 gives us an acceleration of 4.63. Right? So they're not accelerating, right, at 9.8 meters per second squared, because that would be your skier falling off a cliff and going into free fall. Right? Instead, they're accelerating with some component of g. Right? This acceleration down the ramp, which is 4.63 meters per second squared. Alright, from there, you have yourself a simple kinematic problem. Right? We know initial velocity, we know distance, we know acceleration, we want to know velocity. Right? So now we're just treating this as a one-dimensional problem, and that one dimension is parallel to the inclined plane itself. Right? It's a downhill dimension. So we got x, we got a, we got v naught. We want v, we could use v squared equals v naught squared plus 2ax. Where our unknown v is equal to 0 plus 2 times 4.63 meters per second squared times 360 meters. So you solve that out. So 4.63 times 2 times 360, take the square root, and we get 57.7 meters per second. Right, so the key to these inclines is recognizing that only some portion of that gravitational acceleration exists within the dimension of the incline itself, right? And thus only part of it is responsible for accelerating objects down an incline. Now what I want you to do is pause the video here and look at the next example on the next page. So in example 3.7, you got the speed of a roller coaster. A classic wooden coaster has cars that go down a first big hill, gaining speed. The cars then ascend a second hill with a slope of 30 degrees. If the cars are going 25 meters per second at the bottom and it takes them 2 seconds to climb this hill, how fast are they going at the top? So pause that here and see if you can't start setting up the problem. Right? Get as far as you can on your own. And when you get stuck, resume the video and watch the walkthrough. Alright, let's start setting this up. Now, again, we've got ourselves an inclined plane. Now remember, you get to set the scope of your vision in physics problems. We don't care about that first big hill at all. The only thing we care about is the second hill that it's trying to ascend. So we know that that roller coaster, right, is trying to ascend the second hill. We're also told that it approaches this hill with an initial velocity of 25 meters per second. And we want to know our final velocity up here, given the fact that it takes 2 seconds to make it there. And we're also given the fact that the slope, that the incline, right, is at 30 degrees. So we can always start by finding our component of the gravitational acceleration that exists within the plane of the ramp. So again, we would use the sine function. So the sine of 30 is equal to opposite over hypotenuse. So 9.8 times the sine of 30 gives us 4.9 meters per second squared. So we know that our acceleration has a magnitude of 4.9 meters per second squared. Now I said magnitude for a reason. We still have to determine the direction. We know this cart is traveling upwards. Now typically what I do, because it makes my life easier because it limits the amounts of negatives you have to worry about, is I make whatever direction the object is going your positive direction. So if the object, like the last example, the skier, is going downhill, I make downhill your positive direction so that most of your variables are positive. If the object's going uphill, like the roller coaster, I make uphill my positive direction because, again, it limits the amounts of negatives I've got to keep my eye on. So if we're considering uphill our positive direction, which is why V naught is a positive 25, we've got to consider the direction of the acceleration. Well, G parallel is always going downhill, right? So we would have to pop a negative in there. Now your mathematics would warn you if you made a mistake in putting a negative, right? If you somehow came up with the final speed greater than 25 meters per second, that should set a red flag going off in your head, because is it possible for a cart that's just rolling up a hill to gain speed? No, right? That's physically insane, right? So let your math, check with your gut. Does it make sense to you, your mathematical solution? If not, go back and try to look through your work and think, did I account for all of my directions? So this is negative. All right, from here, again, it's just a simple kinematics problem where V equals V naught plus AT. So V equals 25 meters per second minus 4.9 meters per second squared times 2 seconds. So V is equal to 25 minus 9.8 gives us 15.2 meters per second. And again, do a gut check. Okay, that's less than 25. That's good. That's what we expect. All right, we expect a coaster to slow down on the uphill. Now let's look at that conceptual example down at the bottom. I'm going to pull that document over here. So take a second, pause the video, and take a look at that and see if you can't figure it out on your own. So we got a block of ice that slides down a ramp. For which height and base length is the acceleration the greatest? So they give us a selection of bases and heights. Now there's a few different ways to look at this. You can look at it in terms of ratios, but I find it simplest, especially for beginners, to be a little more careful and a little more detailed. So we know that the acceleration is going to be based off of that angle theta. Right? We're given an opposite side. We're given an adjacent side. Right? If you look at your trig functions, tangent of theta equals opposite over adjacent. So theta equals inverse tangent over opposite over adjacent times opposite over adjacent. And so what you can do now that you've rearranged your equation is just quickly pop these into your calculator. Right? Find the angle for each one, and whichever one has the greatest angle is going to have the greatest rate of acceleration. Now I have uploaded on Google Classroom a pre-lab. So what I want you to do is read the problem, think about what kind of materials you would need, what your experimental design would look like, so sketch it out, and write a procedure for it. And the next live engagement session we can talk about that pre-lab. And then what we'll do is I'll film me collecting the data, and you'll have the rest of the lab to do based off of the data that I've collected for you. But yeah, hope that helps. Send me an email if you got a question. Come to live session.